Good morning / afternoon, everybody. Today, I'm going to spend about 20 minutes of your time, which I'm very thankful you've chosen to spend with me, talking about tests and types, which is a pretty generic name for a talk, and I apologize for that. And I would certainly welcome any feedback on a spicier title after this talk from any one of you. But anyway, tests and types. We all know that we should be doing more tests. And in the context of this talk, when I discuss testing, I'm talking specifically about running and writing automated testing suites, largely with a focus on the dynamic language we all know and love, JavaScript. And I'm also going to be discussing what I would say is the more conventional suite of tests. So that's predominantly unit and integration testing. I am not nearly galaxy brain enough to have spent much time with things like fuzz testing or property testing. And when it comes to types, I'm going to be talking about static typing with regards to TypeScript, because JavaScript is now obviously also everyone's favorite compiled language. And my main motivation today is to encourage you to think about using static typing to complement your existing test suites. So this is probably mostly relevant to JavaScript users, but there's also projects like Sorbet for Ruby. And of course, Python includes typing in its standard library now, because of course it does. Python is batteries included. But I'm also motivated to encourage you to think about how you've approached testing in the past, and maybe even to rethink some of your attitudes towards it. Because I think historically, we've all been a little dogmatic about testing. And I believe a software team is at its best when it's functioning as an empathetic, curious, considerate group of people. And I'm also motivated by the thought of giving this talk itself. I have always been incredibly nervous about discussing testing in the open. And nothing in software has made me feel more like an imposter than when I've actually been involved in discussions around testing. So, and this gives away how old I am, but in the spirit of the 90s song, Everybody's Free to Wear Sunscreen, I am doing one thing today that scares me, and it's this talk. And so we're gonna start by taking a high-level overview of testing and types. We'll consider how they work together before looking at some real-world examples of how they helped me and the rest of the team out on a recent client project, and also some ways in which they have not helped us out. And so why we test, or why I test a lot of the time, is to get confidence that I'm not going to introduce regressions into my code, to get confidence that I'll be able to add new features in the future without doing the regressions from the first point, and confidence that my code is in fact sort of correct and it sort of hits the requirements that I need it to. And so here I'm not specifically going to be thinking too much about tests as a way to inform and influence, sort of actively influence our design. However, that is perfectly valid and something I do encourage. But I'm obviously going to start by talking about FizzBuzz. I know that FizzBuzz has been done to death. The requirements are to write a program that prints the numbers from 1 to 100. But for multiples of 3, we print fizz instead of the number. And for multiples of 5, we print buzz. For numbers which are multiples of both 3 and 5, we print FizzBuzz. Now, I'm not going to show any function bodies or any actual test code, but instead we'll just think about the tests that we would be writing to ensure the correctness of this program and to give us the confidence that we need. So imagine if we invoke our FizzBuzz function with a 3, we get a fizz. So we'll write a test for that. And if we invoke our FizzBuzz function with a 5, we'll get a buzz. So we'll write a test for that. And with a 15, we'll get a FizzBuzz and we'll write a test for that. And then maybe we'll throw a 45 in there as well for good luck, and we'll put that in our test suite as well. And at this point, we feel pretty confident, pretty good about the work we've done. Our 4 examples have combined to give us this sort of warm, comfortable sense of confidence. I press the slide button here, and I don't think it's actually gone to the next slide yet, which is really quirky. So we'll see if there we go. And our 4 examples have combined to give us a warm, comfortable sense of confidence. We now believe that our software is a fully functioning product that adheres to those requirements and can be released into production. In this context, our tests are examples that we've used. But this may not always be the case. So with a fizzbuzz of 52, for all I know, the application here will collapse. Or if I call fizzbuzz with a string of hi, or if I call fizzbuzz with JavaScript's most preeminent type, undefined, and again, I'm not entirely sure my slides have updated even though I pressed the button. So we'll give it a second to come in. There we go. And then also, if we send in a -1, I'm not quite sure what the behavior will be in this application yet. Or I have no idea what would happen if we sent in what would normally be considered a floating point number in literally any other language, 25.5. And it's at this point that the wonderful 8-light designers who made our slide deck are getting really furious with me because we're starting to overlap the logo in the top left. But what about if we sent in a 103? The behavior of the application with these examples is still unknown. We've only been able to assume the correctness from the small sample size that we've used to do our testing. And we've specifically selected our examples to give us a feeling of confidence, a feeling of correctness. We may be right, but we may also not be right. And generally, I find that's how I introduce bugs into my code. You can, of course, test for this correctness. You can check at runtime. You can throw exceptions. You can add all of these cases directly into your test suite. But writing more tests is more time, and it's more maintenance, and it's more work. On the critical paths through your application, this is pretty universally considered to be a price worth paying. But what about your less critical paths? And what about when your non-critical paths then accidentally collide with your critical ones? Which, in a roundabout way, now brings me on to types. It's 2021. Types are awfully vogue right now and have recently been considered the answer to all of life's problems. So you may not have used a type system before, and there's a lot of nuance between them. So I'm going to be sticking with TypeScript. Whereas JavaScript has a series of permissive primitives like string, number, and object, the language doesn't actively check that these types have been used consistently. TypeScript does enforce this consistency statically before your code ever even runs. So in the first example, I define a variable called name, I declare it to be of a string type, and I assign it to my name. Now, when I try and reassign that variable to a number of 222, the compiler is cross, and it tells you that number is not assignable to type string. Unlike some other statically typed languages, TypeScript has a pretty nifty ability, however, to infer those types. So in the second example, we don't have to explicitly declare that year is a number for the compiler to pick up on it and start complaining. Generally, I find that static typing is having something that enforces the boundaries of our functions. It's like having a doorman at the front of the application, turning away people wearing the wrong type of shoes. And it's also like having a guard at the end of the function that's not letting anyone leave unless they're still properly dressed. So with this visual representation, for instance, only apples are allowed in and only oranges are allowed out. The rigidity of the compiler is shaping our understanding of the function. And that rigidity is also being used to give us confidence and give us that sense of correctness in our application. But even with a type system, it can still be really hard to understand what's going on inside. We'd like to think these details are not always relevant, but underneath the hood here, this visual representation is turning the apples into lemons and the lemons back into oranges. Back into oranges? Into oranges for the first time. This may not be relevant, this may not affect the correctness, but it may affect the correctness because sometimes we can just be plain wrong. This function, sum two numbers, takes two arguments, and returns a value that is definitely not the sum of them. The type checker knows that numbers are going in and numbers are coming out, but it has absolutely no way of giving us confidence and correctness with what's going on inside. Bad. Now, just in case you're thinking that such things could only be a problem with a silly transpiled language like TypeScript, you can be equally as wrong in really smart languages like Haskell as well. So how does this help our FizzBuzz problem? Having a number type check on our FizzBuzz function only directly removes two of these considerations away from us. We can only use the compiler to enforce the numbers that are going in and that numbers are coming out. Now, I may sound like I'm being pretty down on types here, but I absolutely am not. I love them and I'm a massive fan. And this may not look super valuable on this incredibly trite example, but by putting in the upfront work to wrestle with the additional syntax of a type system, this actually helps us minimize entire categories of potential errors that could routinely ruin our mornings, afternoons, and evenings while designing our applications. And if you'll allow me, I'm going to take a quick sideways detour to talk about my own personal experience of incorporating TypeScript into a couple of projects over the past year. Knowing the constraints of a type system meant that I lost my confidence when my functions had to do too much conditional logic. I wanted my data to adhere to the right shape and category. And this sort of encouraged me to naturally sort of push all of my logic into a central domain. And it encouraged me to avoid using conditional logic when it was unnecessary. And this is obviously good practice without a type checker, but with static typing, my design was sort of naturally guided this way in a way that object-oriented programming with duck typing just never quite did it for me. There I often modeled sort of my code entirely around encapsulation. And I often found myself confused with many tests and an application that still didn't work. Now I know what I'm actually doing here is admitting to you that I'm chronically bad at object-oriented design and that I also totally lack discipline when writing my test suite. But I actually find one of the nice things about having the type system is it's a bit like you've got a little computer buddy sitting at your side, helping you do all of this. For instance, if we sort of imagine that this little orange blob represents a front-end React application, this dot here is our domain zone. In here is all of the main front-end logic of our application, all the authentication calls, all of the code we use to process payments, everything to do with making myriad API calls. We use our types here, of course, but we also thoroughly test this part of the application. And we feel confident in our code because of it, and life feels really good. And then we can surround that with all of our presentational components. These don't contain much logic at all. And so our type system is sitting at the door and it's calling us out if we pass in the wrong props. We can still be confident in the code here without standing up an extensive test suite. That's my main argument today. And I also think this isn't something to be afraid of. I find it gives us more bandwidth to put more testing effort into where our tests are needed the most. Now, this is based on a component we did on a recent client project, but in the interest of not breaking any NDAs, I've replaced it with Pokemon, which is a wonderful series owned by a particularly litigious company. So we'll have to see if the recording of this talk lasts for any length of time on YouTube. I'm sorry if it doesn't. But here we have a functional React component that receives a Pokemon object as props. It restructures its values, it destructures its values out of the function signature, and it returns a div containing the Pokemon's name and image. Now, I've worked on projects and written tests for components like these where we validate the props input. And sometimes we even shallow render and assert that the right props were handed in. There's been good code coverage, and we felt pretty good about it. But this has taken us quite a lot of time. And there was a maintenance cost every time we make changes. And in these projects, we ended up making changes fairly frequently. I'm not saying this isn't work worth doing, but TypeScript can take care of this for us. We don't need to worry about it so much. If we pass in the wrong props or change the API, the TypeScript compiler will alert us straight away, even quicker than all but the most lightning fast test suite. And as I've already said, I'm not so great at writing tests. My test suites are rarely lightning fast. Now, there are caveats here. There's an obvious problem in this component where we don't have anything really in place to check that our sprite value is or is not a real URL. And I'd want to mitigate that to feel totally confident. And on this project, our front end was relatively small and featured only a few dozen total components. And we also used a popular UI framework for our raw building blocks as well. So this may not work in your use case. I'm not trying to suggest that we can always do this. And the other big problem with this approach is that we have nothing here that really takes care of how our components look when they're actually rendered. But this, I think, is something that testing really struggles with at the best of times. And I have never in my life used a snapshot testing system that I did not find agonizing. In this project, we tested the visuals manually when we issued PRs. Now, this relies on fleshy humans and is therefore massively error prone. But like I said, we didn't have too many components at this time. And so this was work that we felt like could be managed. And honestly, I think that choice felt right to us. And satisfyingly, we didn't really encounter any problems on this project by doing things this way. My opinions could and probably would be massively different if we hit massive pain points. But here we felt good. And I would almost certainly lean towards doing this again on another project. And again, this is a dramatically simplified example, but we could also apply the same thinking to our backend root handlers. Here we're making a GET request to a Pokemon ID endpoint, and we've removed some of the unhappy path, specifically what happens if we cannot pass the ID parameter into a correct Pokemon ID. But by using a type system to push the logic into that central domain, which in here is our get Pokemon function, we get automatic confirmation that we're using our application correctly. And so here, we felt comfortable easing off on test coverage in this area. Now, most of our handlers didn't spend much, if any, time performing that dreaded conditional logic, but instead they just ferried the request to and from our domain logic. And TypeScript ensured that we were correctly calling our conditional brainy code in our domain. Again, it worked really well, and we encountered minimal defects in production. Now, I don't think you can use any tool without encountering a few gotchas. And we did hit a couple of very painful points when using TypeScript in our domain logic. And I think it is only right that I share some of those. Back on our front end, there are parts that TypeScript can't reach. We had critical code in our application which called out to a backend service to retrieve information with a fetch request. We turned that response into JSON, and then we lightly transformed that JSON into an inferred type usable by the rest of the front-end application. Now, TypeScript exists on top of JavaScript and is compiled away to not exist at runtime, but it does contain what is seen as the as keyword. This is commonly understood from its use in other languages to be a cast operator, which is to say it converts one type to another. In TypeScript, it is a type assertion, and it essentially tells the TypeScript compiler that you can personally vouch for this type to be what you say it will be. Now, when data is coming from an external service, that is a foolish thing to do. Our data in this instance is not a Pokemon response from server type. It is unknown. This here led to numerous silent failures whenever the contract between the front end and the back end changed. One of our errors was so critical, it led to the entire front end application simply not rendering at all, as we didn't think to gracefully handle this, as we assumed that we were type safe. Even worse, we mostly used a series of type conforming stubs in our local development environment. So we only started seeing this pain once we started deploying changes. This created some disharmony between people working on each side of the application, and it slowed us down. I would say it was an enormous whoops. The solution we found, however, and in the interest of full transparency, we did not get a chance to implement it, was IOTS, which is a runtime validator leaning on the purity and rigor of functional programming that I barely understand. This is the most complex slide of the talk, and we're going to shoot through it together. So IOTS is the little T functions in this slide, and it creates what it calls codecs. And these are runtime values that represent static types. And again, just to emphasize this, our static types do not exist at runtime. Our const for Pokemon here is the codec, and this can also provide static type information to the Pokemon type thanks to IOTS. These codecs return what in functional programming I believe is called an either type, which is a type that represents either failure on its left-hand side, which here it turns into a specific errors object, or success on the right-hand side, which here is our decoded Pokemon type. The fold function, when used with an either returns the error or the success value, depending on what came back. And the pipe function here takes the output of the first function and applies it as an argument to the second. Now, these are fun, feisty functional programming concepts that I do believe are well worth a look. But what we're doing here, however, is leaving the functional programming world behind as soon as we possibly can. And we turn our successes into a resolved promise, and we turn our errors into a rejected promise. This is enforced at runtime, thanks to the IOTS library. Now, amusingly, I was once passionately detrimental to the idea of a runtime type validator that a team implemented on a PHP code base in a previous client project, which conceptually is a pretty similar idea to this, and is yet another piece of evidence in my belief that all ideas in technology will eventually be right. And the reason I wanted to show you this is that it exposes one of the hardest things I found about using TypeScript in a production application. You end up becoming incredibly distrustful of anything that could come in from outside of your beautiful, manicured TypeScript bubble. And if you don't, everything can very quickly collapse like a souffle, and your confidence can quickly evaporate. Another big gotcha for TypeScript, especially compared to many other static type languages, is that TypeScript is structurally typed rather than nominally typed. And what that means is it does its type checking based on the contents of its objects. So here, Pokemon Trade and Pokemon Lookup are structurally identical. So one type can be used in place of another, even when that may end up causing confusion in the code base. Now, this is a conscious decision by the TypeScript designers to ensure that TypeScript can build upon all of the JavaScript code in the world. And it means you can do things that you might not be able to expect to be able to do, especially if you're used to some other languages. It is intentionally designed to be an unsound typed language. And that's not necessarily a bad thing, but it means we need to keep all of this in mind when we design with it. Otherwise, we may end up in a really sorry situation. I find this also means that types are sometimes a little too broad. And if we mix up our structural typing with JavaScript's relatively light amount of base types, we end up with types that are sometimes way too broad for our domain. Here, we have a Pokemon trade type that takes a UUID, which, because of the small amount of types available to us, we've basically forced to type as a string. And unlike in, say, Java, where we have a UUID type, here we can please the type checker with a value that is decidedly not a UUID. This can be problematic in certain areas, areas like this, and also maybe anywhere where you need a really strict value, such as an ISO date string. Now, one of the answers commonly used in the TypeScript community is to apply what is commonly called a branding, a type branding, to emulate nominal typing. Here, brand is a generic type with two parameters. The first type parameter, t, represents our base type, and the second type, u, is a tag we use for our branding. The resulting type is an intersection of an object, is an intersection of the base type with an object containing that brand property. This means that we can't get those, that problem we had earlier where we could assign types to another type. And this can also be enhanced with, say, parser functions that can guarantee conformity at runtime. And again, you may be thinking, like, all of this sounds like an enormous amount of workarounds. It's extra maintenance work. It's code that we've put in that we have to use to enforce things at runtime, and things that can feel a little bit hacky. And how on earth can we accommodate all of this? And the answer, of course, is tests. We've gone sort of full circle. Like, I've suggested we write tests to get confidence in the things we do to work around the constraints of our type checker, after originally suggesting that we use types to remove some of the tests we need to write. We've sort of gone a little bit symbiotic. But would I use TypeScript again? Like, I absolutely would use TypeScript again. Using TypeScript on our last project helped cut down the tests we needed to write and allowed us to focus on writing better tests for our critical paths. And so much so that when refactoring a project the other week, I changed hundreds of lines of code across dozens of files without really running the test suite at all. And the changes worked first time. It was absolutely terrifying. And is working this way the only solution? No. And is it really actually like a debate between tests and types? I don't think so. Like, this is, we've ended up having a conversation about design and using tests and types to help influence our design and make our design better and more robust. And this is something that worked for me, and maybe it's something you might want to try on your next project as well. And the thing I've really been talking a lot in this talk is, talking about a lot in this talk, is confidence. And I don't think confidence should like stop at our tests. I want our tests to make us feel good outside of the code itself. And I want our tests to make us feel confident with our decisions, our choices, and the honesty that a lot of the time we're still figuring all of these things out, especially our testing. I talk to a lot of bootcamp grads who are so passionate and hungry about joining our industry, who are kind of fearful about asking questions about tests because they don't want to make a bad impression. And I really don't think things should be that way. And I think if testing was something we could prescribe a handful of universal rules towards that guaranteed success in all applications and correctness in everything, we'd have cracked it by now. So the fact that we still discuss these things shows that it's never quite as simple as any of us would probably like. There is no real testing equivalent of the idea that we should just floss more because it's good for us. It is okay to keep trying things out. And at the end of the day, tests and types should just influence our design, and we shouldn't be beholden to either of them. Thank you.